proofs? What kind of proofs? Sure. Yeah. Can we print out? Yeah. 와서 가져가세요. Come pick it up from here. Yeah. So what and what? Direct proof and indirect or indirect. So direct proof is sometimes called proof by what? Definition, right? So usually direct proof is used usually for what kind of statements? Conditional statements. What are conditional statements? If P, then Q, or P implies Q, right? So how many kinds are there in the indirect proofs? Indirect proof. By contradiction. 이건 뭐라고 했죠? 무슨? By, what's the second one? Contra positive. 이건 뭐라고 했죠? 대우, right? So in the contradiction, you assume same condition. P stays there, and you assume, you do suppose. Suppose what? What do you suppose? Suppose not Q, and then you arrive to a contradiction. That's the proof by contradiction. What was by contrapositive? To show this, instead of showing that, you show what? Not Q implying not P. That was contrapositive. Yes? So let's do the induction today. So we'll do mathematical induction and binomial theorem today. 수인 가져가세요. Yeah. So let's read. 시작. Mathematical induction and binomial theorem. So, to prove a statement that is true for each positive integer n, the proof technique mathematical induction is devised. So, what is positive integer? What are positive integers? Give me some of those. 자연수, right? 1, 2, 3, 4, 5. These are positive integers. Yeah. So we call them natural numbers. Why are they called natural numbers? 왜 이게 자연수일까요? 카운트할 때 하나, 둘, 셋, 넷 이렇게. We count 1, 2, 3, 4. So natural. 맞죠? 그래서 자연수입니다. 자연스럽게 카운트하는 거. So those are called natural numbers. So, for example here, let's look at this statement. 읽어볼까요? 시작. Show summation I equal to 1 to n, 2i minus 1 is n squared for every positive integer n. So what's my variable here? I. So for every positive integer n, so I'm going to fix n. Right? So when n is 1, we have to show summation I 1 to 1, 2i minus 1 equal to 1 squared. Right? When n equal to 2, we have to do I equal to 1 to 2, 2i minus 1 equal to 2 squared, etc. But we have to do this how many times? Infinitely many times. Why? Because we have to show this for every positive integer. Is it possible? That's impossible. So how do we know whether this is true? Right? So that's the question. So this is a statement concerning n, is that right? This is the statement that is true to prove a statement. So this is a statement concerning n, every positive integer n. Yeah, so to prove such a thing, we have mathematical induction. So this is our statement. S of n. It's a statement. S doesn't mean summation. 여기 S를 summation 얘기하는, sum을 얘기하는 게 아니에요. S is the statement. S of n is the statement concerning n. Concerning concerning statement concerning n. 이거 됐어요? 야, 이게 n에 관련된 statement라는 거예요. Yeah. So how do we show if this is true for each n? So state what S of n is. And then we're going to use the properties of natural numbers. Natural number의 property를 보겠습니다. 자연수의 property. Okay? 자연수는 일단 뭐가 있어야 돼? 일단 1 있어야 되고 1이 있으면 그 다음에 1에다 1 더한 것이 있어야 돼. 2가 있고 2가 있으면 그 다음에 2 plus 1 이것을 어떤 n항이라고 부르면 일단 1은 있고 if there is n term, n plus 1 term should be in the set. 2가 있으면 그거에 더한 것도 있어야 되고 3이 있으면 그거에다가 1 더한 것도 있어야 돼요. If this is true for any arbitrary n that I take, I'm going to choose any n from this set, and if n plus 1 is also in the set, then I generate all natural numbers. So, this is the characteristic or properties. So, first of all, we have to have 1. Yeah. And star should be true. Stars read, given any number in the list, call it n. Its successor, n plus 1, is also in the list. If this is true, then the list includes all natural numbers. So I'm going to build a one-to-one relationship between the statement S of n and the set of natural numbers. 1대1 대응을 시켜요. 여기에다가 1 넣어서 when I plug in 1, if this is true, that means 1 is in the set. And I'm going to assume that n is in the set, so that means S of n is true. I'm going to assume that S of n is true. S of n이 true라면 그 말은 n이 셋 안에 있다면 now I have to show somehow I have to prove that S of n plus 1 is also true. 그러면 n plus 1도 셋 안에 있기 때문에 모든 natural number에 대해서 true이다 이렇게 얘기할 수 있어요. So that's the induction. Okay, so we build one-to-one correspondence. 1대1 대응, one-to-one correspondence between the set of natural numbers and statement Sn 사이에 1대1 대응을 시킵니다. Okay, so for example, when we apply this to this problem, the example, so what is S of n? S of n, 여기 equal 하면 맞을까요? 틀릴까요? 이거 맞을까요? 틀릴까요? 틀려요. 왜 틀려요? S of n은 이것이 같다는 말이죠. S of n이 얘랑 같은 건 아니잖아요. Right? S of n doesn't equal to this. S of n is the statement which says this equals to this. Okay? So you cannot use equal sign. So be careful on that. So don't use that. You can say let Sn be the statement I equal to 1 to n, 2i minus 1 equal to n squared. Or you can say, let Sn dot dot summation I equal to 1 to n, 2i minus 1 equal to n squared. So do not use equal sign between this and this, because that's the statement. 여기 됐나요? Is that clear? Yeah. So we want to show that this statement is true for every integer, every positive integer n. So 1은 항상 있어야 되죠? So we'll plug in 1 into this and we will see if this is true. Okay, so check if 1 is there. So we'll plug in n equal to 1. So that is S1. Right? So this is summation I equal to 1 to 1, 2i minus 1. I have to check. So this is a question mark. I have to check whether these two are the same. Okay? Yeah. So what do we get on the left hand side? 2 times 1 minus 1, we get 1. On the right hand side, we get 1. They are same. So S1 is true. 그 말은 in my set, what is in there? 1 is in there. 그 말이에요. Now we produced 1. 정말. Yep. So now we will assume n is in the set. n 있으면 we have to show what? n plus 1 is in there. So this is assumed. We assume n is in the set. So given S of n is true, we have to show S of n plus 1 is true. Then we're done. 이해하겠어요? Yeah. So number 2, we will assume, this is our assumption. So this is if condition. Assume Sn is true. So we'll show, what do we have to show? S of n plus 1 is true, right? So proof for this, what is Sn plus 1? Summation I 1 to n plus 1 2i minus 1. Is this equal to n plus 1 squared? That's the question, right? So to show this, we use what is given. We know that Sn is true. So how can I break this sum? Summation I equal to 1 to n, and then I can separate the n plus 1 term. And to use our assumption. Yeah. So I can write this, the left hand side, as summation I equal to 1 to n 2i minus 1, and I can separate out the last term. That will be 2 what? n plus 1 minus 1. Fine? Okay, so because S of n is true, that was our assumption, so we know that this equals to what? n squared, right? n은 셋 안에 있다고 가정하고 하는 거예요. Okay? So this is equal to n squared because Sn is true because of our assumption. Yeah. So this is equal to, then we get n squared plus 2n plus 1. Agree? Yeah, if I simplify everything. And is there indeed n plus 1 quantity squared? Yes, it is. So what does this tell you? 지금 여기서 얘기하는 게 뭐예요? n이 있으면 n plus 1도 있다. 어떤 n이든지. So this can generate set of all natural numbers. So we can say S of n is true for every positive integer n. So as the conclusion, by mathematical induction, S of n is true for, 이거 이제 잊어버리면 안 돼. 이거 다 하고 나서 이거 꼭 써줘야 돼. For every positive integer n. By mathematical induction, S of n is true for every positive integer n. 하는 것들이 다 true임을 보이려면 그 넘버부터 시작하면 돼. 그 넘버부터 시작을 하고 그 넘버가 for example if it starts at -1 then s minus 1 is true 보이고 then we assume sn true and then you show sn plus 1 true. It still builds one-to-one relationship between natural numbers and s of n. Okay, so let's look at this example. 시작. Define a function recursively for all positive integers n by f of 1 is 1, f of 2 is 5, and for n bigger than or equals to 2, f of n plus 1 is f of n plus 2 f of n minus 1. Show that f of n is 2 to the n plus minus 1 to the n. So what is s of n for this one? What's the statement concerning n? What do we have to show? This is what we show, right? So Sn is Fn is 2 to the n plus minus 1 to the n. From where? Where? Define a function recursively. So this function is defined at 1, defined at 2, and from n equals to 2, this equation defines x of 3. Right? So it is defined for each integer n, and we have to show that this is true. That formula is true for every positive integer. So this is the statement to show. What's the starting number? What's the starting number for this S of n? 1. 1부터 시작하는 거 아니에요? 맞죠? Starting number for S of n. So the starting number is 1. So we have to show 1 is in the set. So S1, we'll see if this is true. So f of 1 is 2 to the 1 plus minus 1 to the 1. And we have to show this equals to what? What is the given f of 1? 1. So we have to show if this is equals to given number 1. Is that true? Yes. Yes. So S1 is in there. So S1 is true. 됐어요? Fine. And then what's the next step? So we assume Sn true, have to show or will show, have to show what is true. Sn plus 1 is true. Fine? Okay, so here to show this, we have to use which formula? To show this, we have to use this, right? Sn is true. So Sn is true, meaning Fn is this. So f of n은 이건데, 그 다음에 f of n plus 1은 여기다 n plus 1 넣은 거랑 똑같다 보이면 되죠? So when we do that, we have to use which formula? So we will have to put f of n plus 1. So here to show this, Sn plus 1 is the following. Fn plus 1 equal to, does that equal to 2 to the n plus 1 plus minus 1 to the n plus 1. 이거 보여야 되죠? Yeah. So look at this problem. To show this, which equation do we have to use? Which condition do we have to use? We have to use this, and what else? Fn plus 1 equal to this. There's another condition that we have to use. But this condition starts at n bigger than or equal to 2. That means this number is what? 이 넘버가 언제부터 시작할 수 있어요? 저 보면은 3부터 시작할 수 있어요. 이 넘버 n plus 1이 3부터. We can use this formula when n plus 1 is 3. Right? So, in the basis step, we need one more condition. We have to check S2 is also true. 1 is not enough because we can use this formula when this gets to 3. So that is the difference between this example and the previous one. So because to show this, we have to use this formula. We have to use the given formula, that is the given relationship, Fn plus 1 equal to Fn plus 2 f of n minus 1. We have to use this. But this is true for n bigger than or equal to 2. So, when it hits 3, I can use this formula from 3 and on. Then I need condition on F1 and F2. F2 and F1. Right? So, because for F2 and F1, this formula does not apply, I have to check whether S2 is true in the beginning. 그러니까 여기서는 1만 있으면 안 되고 1 다음 2 있는 것까지 assume하고 해야 돼. So let's see if S2 is true. Okay, so F1 is this. For S2, F of 2, 2 squared plus minus 1 squared, does that equal to, what was the given value of F2? 5. Is that true? Yes. So S2 is also true. So S2 is true. So in this assumption, 그 다음에 assumption은 뭐부터 가는 거예요? 1, 2는 체크를 했고 이제 n은 3부터 가는 거예요. 3부터 했을 때 얘가 true라고 가정하고 그 다음 걸 보면 돼요. Then we can use this formula. So assume Sn is true for n bigger than or equal to 3. And we will show that S of n plus 1 is true. We need this condition because this relationship only applies from when this number is bigger than or equal to 3. Okay? Yes. So that is the second principle. Second principle 하고 이거 와서 끝내겠습니다. So sometimes we need conditions before n. So that is the second principle of mathematical induction. Okay, let's read. 시작. S1 is true and double star holds. So this is the double star. 시작. Given Sn is true and S of k are true for all k 1 to n minus 1. Sn만 true라고 가정하는 게 아니라 그 전거까지 다 true라고 가정을 한 후에 Sn plus 1이 true인 것을 보이는 거예요. See here, to use this formula from n bigger than or equal to 3, this is Sn, 맞죠? And what do we have to know? Sn minus 1. We have to assume Sn and Sn minus 1 are true. So, in this assumption, Sn true, and we also have to assume Sn minus 1 true. That is, we're using the second principle. So, 다시, let me explain this fully and then we'll come back. Okay, so S1 true, and then Sn is true, and all the previous ones are true. Then Sn is true for all natural numbers n. So let me tell you why this generates all natural numbers. 이렇게 하면 왜 전부 natural number가 되는지를 보겠습니다. So let's look at the justification. 일단 what is in the list? 1은 있어요. 왜요? S1이 true라고 했습니다. So S1 is true. 이것 때문에 1 is in the list. And suppose it satisfies double star. So given Sn is true and Sk are true for all k starting from 1 to n minus 1. But n is 1. n이 1이기 때문에 n 전에 거는 있어요? 없어요? 없어요. n이 시작 넘버니까. But by double star, 이것을 만족하면 what is also true? Sn plus 1 is also true, right? 그래서 뭐가 또 리스트에 가는 거죠? 2. So by double star, 이것이 true라고 했기 때문에 2 is in the list. 여기서 k는 없어요. n이 1이니까. K starts at 1, right? It ends at 1, so there's no K. There's nothing to apply. So 2 is in the list. 됐죠? So now 2 is in the list. Okay? So let n be 2. n이 2라고 하면 double star를 만족하니까 what's in the list? 1 and 2. Okay, K starting from 1 to n minus 1 are in the list. true라고 가정하는 거니까 1, 2가 있는 거예요. 그러면 1 and 2 are in the set. So here it is 1. 됐죠? So when n is 2, 1 and 2 are in the set by our hypothesis. So by star을 만족함으로 뭐가 있게 되는 거죠? 3 is in the set. If there are 1 and 2, then 3 is also true. Then 3 is in the set. So we get 3. So on and so forth. So this again generates all natural numbers. So if you need conditions on the previous ones, not only s of n, if you need s of n minus 1 or s of n minus 2, etc., then you have to use the second principle. You have to apply the second principle. Two, yeah. Yeah. Thank you. 2 is in this. Yeah. So let's go back to this one. So we'll start all over again. Okay? So because this formula starts when 3, we have to check 1 and 2. So S of 1 is true. 이거 체크했죠 아까? S2 is true. 체크했어요. That meant F of 1은 2 to the 1 plus minus 1 to the 1, that equaled 1. And F of 2 was 2 squared plus minus 1 squared, and that equaled to 5. 이거는 체크를 했습니다. Right? We check both. 왜냐하면 이 포뮬라가 3부터 시작하기 때문이에요. 그래서 두 개를 체크한 거고 1, 2. And then to use this formula, this involves Fn and Fn minus 1. Not only Fn, it depends on n minus 1, right? So we have to assume Sn is true and Sk is true for all k equal to 1 to n minus 1. 이 assume하고 Sn plus 1이 true임을 보이는 거예요. So we will assume, because this has n minus 1 in there, so we assume Sn is true, or we can say this. We can assume Sk is true for all k. 1부터 어디까지 하면 되겠어요? n도 포함하려고 해요. 두 개 쓰는 거를 한꺼번에 쓰려고. Yeah, I want to combine the two statements. So n 이렇게. Right? So Sn is true and all the previous ones are true. So assume this. And we'll show, what do we have to show? We'll show Sn plus 1 true, right? We'll show Sn plus 1 true. Okay, so in your proof, you can use either one. First principle or second principle. They all generate all natural numbers. So let's do that. here to show, because this formula is true for n bigger than or equal to 3, we'll put n bigger than or equal to 3 there. n bigger than or equal to 2. 2부터 보여야 되는 거 맞죠? 그래야 여기 3부터 오는 게 될 거 아니에요. So n bigger than or equal to 2. Yeah. So Sm plus 1, Sm plus 1 is the following. Fm plus 1, does that equal to 2 to the n plus 1 plus minus 1 to the n plus 1? Is that true? Okay, so left hand side. 는, because n is bigger than or equal to 2, what do we know about fn plus 1? Fn plus 2 fn minus 1. Yeah. This is true because we have this. Yeah. Okay. Then, what is fn? 여기는 n이 bigger than or equal to 2 때문이고, what is that equal to? What's f of n? 2 to the n plus minus 1 to the n. Why? Where? Because we assume this is true for k equal to n plus 2 times what? 2 to the n minus 1 plus minus 1 to the n minus 1. Why? Again, by our assumption. 이거 됐어요? 는. So here I get 2 to the n. I have to produce 2 to the n plus 1, right? 보여요? Here what do I get? 2 to the n, and I have 2 of those. So 2 times 2 to the n, which is 2 to the n plus 1. And then I get minus 1 to the n plus 2 minus 1 to the n minus 1. How do I combine these two to get minus 1 to the n plus 1? This is minus 1 to the n, 1 plus 2 times minus 1. Yeah, right. So this, if I put n minus 1, then we get minus 1, 2. So what do we get? Minus 1 to the n minus 1. 맞죠? Are they the same? Where? n이 0이면 n이 1이면 1 맞네요. Yeah, this is true for what n? n bigger than or equal to 2. They are the same. Yeah. So, last two terms equals to this. 이거랑 같고, 이것은 이거랑 같고, 이것은 이거랑 같아요. For n bigger than or equal to 2, they are the same. Okay, so the conclusion, therefore, S of n is true for what n? For every positive integer n, starting from 1, 2, 3, 4. True for all n Go ahead and do the classwork. Let S sub n be the statement. What's Sn? F1 plus dot 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 plus Fn is Fn plus 2 minus 1. For what n? What's the starting number? We have to show this for which n? For every natural number. 맞죠? So n 1, 2, 3, 4, etc. 이걸 보여야 되는 거죠? Yeah. So S1. What's S1? F1, does that equal to F3 minus 1? Right? So, on the left hand side, what's F1? 1. 왜 1이에요? 주어졌으니까, given. Yeah. Here. Now, how do we obtain F3? By this equation. This is true for n bigger than or equal to 3. So we can use this formula safely, right? So this is, so by this is what? F1 plus F2 minus 1. And what's F1? 1. What's F2? 1. 기분이죠 이것도? Minus 1 we get 1. Is that true? Yes, this is true. So S1 is true. So S1 is true. 여기 됐나요? Now, do we need to check S2 or not? 여기는 second principle 꼭 써야 될까요? 안 써도 될까요? Do we have to check S2? So S2 will involve F2 here, F4 되겠죠. But from this we can use the formula. So when we get F sub 4, we will use the same formula. Is that right? So we don't have to check because we're going to use this formula as the same thing. Same thing is true. So you can show this by second principle. You can check S1, S2, and then you do S sub n true for all k. 그렇게 해도 되지만 꼭 그렇게 할 필요는 없어요. 이 문제에서. You don't have to do that in this problem because this formula applies even from S1. Or you can check, doesn't matter. So S1 is true. So we'll assume what do we assume? Sn true. We'll show Sn plus 1 true. So, 이 n은 뭐보다는 큰 거예요? 1은 보였으니까 right? 여기서부터 시작해야 거 보여야 되니까 right. So we'll show Sn plus 1 true. So what is Sn plus 1? F1 plus dot 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 Fn, does that equal to Fn plus 3 minus 1? N plus 3. So left hand side, 시작. we use Sn true, right? So what's Sn? F1 dot 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 Fn plus Fn plus 1. What do we know about Sn? F sub n plus 2 minus 1. 이거는 왜 같아요? Because Sn is true. Yeah. Plus Fn plus 1. 됐죠? 그런데 이것과 이것은 뭐와 같아요? 언제부터? 지금 n is bigger than or equal to 1, right? Can we apply this formula when n is bigger than or equal to 1? When is this formula true? This formula is true when this subscript here is bigger than or equal to 3. So that means I can apply this when this is 1 and that's 2. 이때부터 계속 apply 할 수 있는 거죠. 맞죠? Yes. So again, this starts at n bigger than or equal to 1, right? So are we safe to apply that formula? What is the smallest number? 2 here, 3, and that will be 4. So we can apply this formula safely. 이거를 할 수 없었으면 그 위에서 베이스 스텝에서 그걸 체크를 했어야 됐어. 이걸 지금 할 수 있으니까, yeah. So we can apply the formula. We can apply the given formula. So this is equal to f what? n plus 3. Because this formula is true. Because this formula fn equals to fn minus 1 plus fn minus 2 is true for n bigger than or equal to 3. And when n is bigger than or equal to 1, this becomes 4, right? So we can safely apply the formula. So fn plus 3, and then we get minus 1. And they are equal. So Sn plus 1 is true. By mathematical induction. That was actually the first principle. Sn is true. Sn is true for all n equal to 1, 2, 3, etc. 질문? Yes. Because here I can apply to prove this. I can apply this formula when n is bigger than or equal to 3. So n bigger than or equal to 1 caused no problem. 그 정도를 그러니까 Sn-1을 사용할 게 없었죠. Sn만 사용해도 됐었죠. To prove Sn plus 1, we didn't use anything below n. 지난 무슨 말인지 알죠? 이것을 증명하는데 Sn이 true만 갖고도 다 되잖아요. 근데 아까 거는 Sn도 사용해야 되고 Sn-1도 사용해야 됐었죠. 그러니까 n 전에 것까지 사용해야 되면은 second principle를 쓰면 되고 n만 가지고 되면 first principle를 쓰면 돼요. Okay. Next. 다른 질문? Any question? So here we didn't use Sn-1. This was the first principle. Next one. Binomial. Okay. So this is a binomial. There are two terms A and B. So when we expand A plus B to the n, this is equals to that. 맞아요? So out of how many A's are there? N. So out of n possible A's. S를 빠뜨렸습니다. A's. Out of n possible A's. A가 여러 개 있으니까. So if we have, for example, if we have A plus B squared, then we get A plus B, A plus B. 맞죠? I can choose A twice. I can choose A here and A there. Then what do I get? A squared. So I choose K, 2. A를 두 번 픽하는 거. And then if I choose A once, right? Then what do we get? A, B, and BA. Order does not matter. 순서 상관없이. Yeah. And if I choose A 0 times, then what do I get? B squared. Then I get all the terms. So out of n possible A's, we can choose K many A's. We can choose K many A's for K what? 0, 1, up to n, right? So this leads to the term A to the K, B to the n minus K. 맞아요? Yeah. When I choose A K times, then B will be chosen n minus K times. With how many possible ways? So you did combinatorics? Combinatorics 하고 있죠? And choose K ways. And combination K. 좋아, 말해 좋아. 자, 이거는 A를 K 추주해서 나오는 것은 B를 뭐 추주하는 것과 같아요? Yeah. Number of ways of choosing A K times is the same thing as number of ways of choosing B n minus K times. So these are equal. And what is the definition of n choose K? 는 n factorial over K factorial times n minus K factorial. So please memorize. And this is true. 그리고 therefore, if I have A plus B to the n, A plus B to the n can be written as, so this is A squared plus 2AB plus B squared, right? So this is the summation of the terms A to the K, B to the n minus K, where K is from 0 to n with the coefficient and choose K. A를 K번 추주하는 방법. 그것을 다 구한 것. Yeah. So this is binomial theorem. We'll use this very, very often. 여기까지 질문? Okay, next. Prime. What's prime? 소수입니다. So an integer, so you have to memorize this definition. An integer and bigger than 1 is called a prime number, is called a prime number, or simply a prime if it's only, for example, if I have 36, what are the factors? 1, 36, 그 다음에 2, 3, 12, 4, 9, 6. Is that all? Yes, really? Minus. 이런 거 있죠? Yeah, and they can be minus numbers, yeah? So, an integer is called prime if it's only positive vectors. We'll look at only positive vectors. So, positive factors. Positive factors are 1 and nothing else. Only positive factors are 1 and n, nothing else. Then n is called prime. When n is bigger than 1. Okay? So is 36 prime or not? Why not? Positive factors are so many other than 1 and 36, right? So an integer n bigger than 1 that is not a prime is called composite. 복합수, composite. C-O-M-P-O-S-I-T-E. 1, number 1. 1 is not a prime. 1 is not composite. Okay? Because 1 doesn't satisfy this definition. So 1 is not prime nor composite. 적을 수 있겠어요? 1 is not prime nor composite. 1은 prime도 아니고 composite도 아닙니다. Any question? Okay. So before we do this, let me look at this definition first. 시작! Definition, let A be in Z. What's Z? Instead of integers. Can they be negative numbers? Yes. And 0, yes. 시작! We say that D divides A if there exists Q in Z such that D divides A. D가 A를 나누려면 나눈다는 것은 remainder is 0. Okay? So what should be A? A should be equal to DQ. Yeah. We say D divides A if there exists an integer. So remainder is 0. So when I divide A with D, what do I get? Q. 나머지는 0. 해서 나머지 0 이렇게 나와요. So minus 3. 이거 맞아요? This means minus 3 divides 24. Okay, so that's the notation. Why is this true? 왜 true예요? 24 equal to minus 3, minus 8. And minus 8 is in where? Z. So it's true. 여기 시작. If B does not divide A, then we write B bar slash A. 이렇게 씁니다. B가 A를 나누지 않으면 so minus 3 does not divide 4 이렇게 됩니다. 됐어요? Yeah. So here. So, is that true? Is this true? What does that mean? 9 divides 36. Yeah, they're all different expressions. 9 is a blank of 36. In other words, 9 is a factor. 좋아요. 인수이다. Factor. 9 is a factor of 36. Good. What else? Divisor. 좋아요. 약수이다. Divisor of 36. Yep. Or, in other words, 36 is a multiple of 9. 36은 9의 배수이다. 됐죠? Yeah. Or, 36 is divided. 나누어졌다? 나누어질 수 있다. Divisible. Right. Yes. 36 is divisible. They all mean the same thing. 됐어요? Yep. So in your quiz or in your exam, you will see many of true-false questions. So mark your answer by true or false and justify your answer. Okay, so here. 시작. For all A, B, C in Z, AC divides BC if and only if A divides B, A and C both non-zero. So first of all, it is if and only if. What's if and only if? If and only if, usually written as if, means P implies Q and Q implies P together. Okay? Yeah. If it is true, then you have to prove. If it is false, if you find a counter example, 발레를 찾으면 false가 되는 거고. Yeah. What do you think? 이거 맞는 것 같아요? 틀린 것 같아요? If I have this, can I go to that? Okay, so let's see. Let's do some scratch. 자, 그럼 AC 나누기 BC. What does that mean? Let's do some. 이게 그냥 scratch예요. What does that mean? 이게 무슨 말이에요? What does that mean? BC는 AC Q. Definition. Q in where? Z. Definition. 됐죠? 는. 자, C를 어떻게 하고 싶어요? 나누고 싶어요. Can I divide by C?
Yes.
Why? C is non-zero, right? So divide by C, because C is not zero. What do we get? B is AQ. But Q is in where? Z. What does this tell you? A divides B? 뭐가 뭐를 나눈다? A가 B를 나눠요? A가 B를 나눠요? 맞아요. Yeah. A divides B. By definition, 맞죠? By definition, by definition. So this is one way. This is one way. Let's see if we can go back. Okay? So we start with A divides B. Then how can I go back? Definition, 맞아요? This is definition. So this is true. So true by definition. So this is what we have. How do I go back? Multiply by C. So here, multiply by C. Then this is what we get, 맞죠? From here, how do I go back? Definition. So 이제 여기까지 해놓고 나니까 true인 것 같아요? false인 것 같아요? true인 것 같아요. So true 하고 이거 이제 proof로 주면 되는 거죠. Okay. 마지막 클래스워크는 숙제예요. I'm going to give it as a practice problem. Yeah. Any questions? Yeah. Bye.